Bom, então vou começar a apresentação do professor David Sokoloff. É um prazer apresentá-lo. Ele é professor emérito da Universidade do Oregon, nos Estados Unidos. Ele começou a estudar física no Queens College, na cidade de Nova York, e ele fez o doutoramento no Massachusetts Institute of Technology, famoso MIT, sob a orientação do professor Ali Javan, que é uma das estrelas da física atômica. O professor Ali Javan é o inventor do laser de hélio neônio, que todo mundo conhece e que a gente usa nos laboratórios de ensino também. Ele ocupou várias posições e assumiu a posição permanente na Universidade de Oregon em 1978. Ele foi presidente da American Physical Society entre 2008 e 2011 e foi diretor da WISTEC, é um centro de ciências em Eugene, no Oregon, na cidade onde ele mora. Ele, há mais de 3 décadas, está trabalhando com pesquisa e metodologia para a compreensão do pensamento dos estudantes e métodos para atingir a aprendizagem ativa. Desde 2004, ele tem trabalhado com a Unesco, liderando uma equipe que apresenta workshops, cursos de uma semana, em vários países do mundo inteiro, particularmente países subdesenvolvidos e em desenvolvimento. Ele esteve na Austrália, no Vietnã, na Coreia, Sri Lanka, Gana, Tunísia, Marrocos, Índia e no Brasil. Se eu não me engano, foi em 2005, foi quando eu tive a oportunidade de conhecê-lo, graças a uma iniciativa do professor Maurício Petrocola. Então, um desses ALOPs, que ele vai mencionar, foi realizado em São Paulo, na Faculdade de Educação da USP. O professor Sokoloff recebeu vários prêmios e distinções, eu vou mencionar apenas algumas. Em 2007, ele recebeu o prêmio Millikan, da American Physics Society. Em 2011, ele recebeu o prêmio da Latin American Physics Education Network e recebeu também um grant da Fulbright para um trabalho na Argentina e também recebeu um prêmio da SPI. A SPI é a Associação Internacional para Ótica e Fotônica. Esse prêmio da SPI foi em reconhecimento aos resultados alcançados, trazendo a ótica básica e a fotônica para o treinamento de professores no mundo em desenvolvimento. Então, é um prazer receber aqui o professor David Sokoloff.
Thank you, Tomas, and thank you to you and the other conference organizers for inviting me. I'm very pleased to be here. I want to thank, sorry. I want to thank my colleagues, Priscilla Laws and Ron Thornton, who I've worked with for over 30 years, and the group that we represent was awarded the American Physical Society's 2010 Excellence in Physics Education Award. And I also want to thank the 2 major sponsors of the research and curriculum development that I will talk about. The National Science Foundation and the U.S. Department of Education. And in the U.S., the National Science Foundation has designated funds within that organization to sponsor research in science education as well as to sponsor basic science research. Here's an outline of my talk. I'm going to speak about characteristics of active learning environments for university and high school physics, characteristics of the technologies that might be used for these courses, and these will be computer-based data acquisition tools, research-validated uses of clickers, video analysis, and the last thing, which is very current, IO Lab, which is a computer-based data acquisition system for distance learning. So to start with, over the last 20 or 30 years, a lot of research has been done on how students learn physics in introductory physics courses. And the physics education research evidence shows that students taught in a traditional manner in their introductory course do not learn physics concepts very well. So maybe it's like Bart Simpson, I will not learn physics concepts. Or maybe you know, maybe you know Sheldon from Big Bang Theory, and he is teaching an introductory physics course, and he spends all his time preparing his lectures so they are perfect and logical, and yet his students don't learn the concepts. By the way, the journal that Sheldon is reading is the American Journal of Physics, which is an education journal, not a physics education journal, not a physics research journal. So what is our proposed solution? Active learning environments. But I want you to understand that it's not just important to learn concepts, but it's also important to learn how to solve problems. And so our active learning environments don't replace quantitative work, but they complement quantitative work. So what are the characteristics of these active learning environments compared to a more passive traditional approach? In a passive learning environment, in a traditional learning environment, the instructor is the authority. The instructor stands up and lectures, and the information flows in one direction. But in an active learning environment, the physical world is the authority. The instructor's role is a guide to help students learn from their physical world. In a passive learning environment, students' beliefs that they bring into the course are not challenged. But in an active learning environment, we use a learning cycle. Students make predictions, they make observations, they compare these, so their beliefs are directly challenged. In a passive learning environment, often collaboration with peers is discouraged, but in our active learning environments, we know that students can learn from each other if they have the right information from the physical world to help them learn. In passive learning environments, experimental results are often presented as facts in a lecture. But in an active learning environment, we use results from real experiments that are presented in understandable ways, and often this is done in real time with computer-based tools. Finally, in a passive learning environment, the lab is a place to reconfirm what you already learned in lecture. But in our active learning environments, the laboratory is a place where often the students learn the basic concepts of physics. Now, sometimes there's confusion about this. Active learning is not just hands-on, because you can do hands-on and not be engaged in active learning. So for example, you can do the most fun, exciting, compelling lab experiment, and that will be hands-on because you're working with your hands, you're doing an experiment. But it's not active learning unless the students are engaged by making predictions and by having discussions. And many of you may know of Eric Mazur's peer learning. Peer learning is a strategy used in an introductory course. It involves no hands-on work whatsoever, and yet it is active learning because it engages the students in the learning process. Okay, so we're going to talk about technology mostly in this course, or how technology can be used for active learning. And there are certain characteristics that the technology should have to be able to enhance active learning. Technology should be easy to use and not require a long learning curve. So these are tools for learning. It's not important for the students to learn how to use a computer or what a computer does, but rather to use the computer as a tool. The tools are flexible and versatile. They're independent of the experiments that you do. They need to have relatively high accuracy. The results need to be displayed in understandable ways, and often this should be done in real time if possible. Students should be able to easily refer to the results that are displayed to justify their conclusions. So in other words, we enable students to observe physical phenomena directly and clearly and to learn from their observations. Okay, first group of tools, and really this is the first group of computer-based tools that were introduced into learning in the introductory course, is computer-based data acquisition systems, which used to be called microcomputer-based laboratories, so MBL. And these consist of an interface connected to a computer and various probes like a motion detector, a force sensor, temperature sensor, current sensor, voltage sensor, and so on, and then software in the computer that allows the measurements to be displayed and analyzed. I liked this cartoon. Hard to keep up with all the technology. In this case, the new technology is fire. Okay, so how do we use these computer-based tools? I will give you two examples. One of how we use these tools in lab, and one of how we use these computer-based measurement tools in lecture. The labs that we've developed are called real-time physics labs. And their characteristics are that they use computer-based tools to help students construct important concepts while acquiring laboratory skills. The laboratories guide the students to construct their models from real observations of the physical world. Not simulations, but real observations of the physical world, using the computer to probe the physical world. The labs are sequenced, so they take where the students are when they come into the course, and they build upon that from week to week. They're designed to fit within the traditional structure of a physics course. So in the United States, typically a lab is 2 or 3 hours long. These labs are designed to be done in 2 or 3 hours. They include a pre-lab preparation sheet, so the students are prepared when they come to lab, and they include a homework to reinforce what the students have learned in the laboratory. And they've been designed so they can be used with the common computer-based data acquisition systems that exist. And there are instructor's guides for these laboratories. There are 4 modules of real-time physics. They're published by John Wiley and Sons: mechanics, heat and thermodynamics, electricity and magnetism, and light and optics. So basically the topics that are covered in an entire year of introductory physics. I want to show you an example. I'll show you just one example from real-time physics mechanics. And I've excerpted a little part. I don't think you can read it. But basically this is an activity. You can see it's activity 3-4. So it's not at the beginning of the lab, it's well into the lab. And at this point, the students are asked to observe the motion of a cart. Let me show you what the equipment looks like. There is a low friction cart. On top of the cart is a fan unit that is blowing towards the right. The positive direction is towards the right. And then there is a motion sensor, which you can't see because my hand is in the way, but it's right where the arrow is pointing. By this point, the students have done a number of measurements with these tools, so they understand how they work. They understand that a motion detector can measure the position of an object at various time intervals and convert those measurements into position, velocity, and acceleration of the object. So they understand that. And this is a more complex motion because what the cart will do is I will give it a push, it will go, and it will come back. In fact, I'll show you what the motion looks like. By the way, of course, in lab, the students do real experiments. They have real equipment. I didn't want to carry all the equipment and worry about whether everything would work right. So therefore, I am just going to show you videos of the experiments. But understand that the students do real experiments. Okay, before I would make an observation, we would ask the students in the lab to make a prediction. In this case, the prediction asks, what will the velocity versus time and what will the acceleration versus time graph look like if I give the cart turn on the fan, give the cart a push, it goes away, and it comes back again. Okay, that's the motion. So they're asked to make a prediction. Then they can make an observation. So here is what this looks like. Give it a push, comes back. I'll do it again, or maybe I won't. Okay, I won't do it again. The computer says I will not do it again. Okay. Now, I'm not going to ask you to make a prediction now. I will in a little while ask you to make a prediction. But the students made their prediction, they discussed it with each other, then they made the observation, and here's what the observation looks like. Velocity versus time, acceleration versus time, collected with the motion detector. Now, we can ask, we don't expect necessarily that students looking at these graphs will immediately jump and say, oh, look, the acceleration is constant and the velocity is decreasing along a straight line. We ask them questions to make sure that they focus on the parts of the graph. So for example, the first thing says, label the graph at various positions. Where did the cart start being pushed? Where did the push end? Where did the cart reach its turning point? Where did you stop the cart with your hand? And explain how you know each of those. So they are directed to look at the graph and learn from it. And then there are a number of questions. And the 2 questions I've shown you focus on the most difficult thing for students to understand. why is the acceleration at the turning point not equal to 0? The vast majority of students will say the acceleration when they predict, will say the acceleration at the turning point is equal to 0. So we ask them, look at the graph. What is the acceleration at the turning point? Why is the acceleration that way? And is the acceleration any different anywhere in the motion? So, make predictions, discussion, make observations, and then direct your attention to the things that we know students naively do not understand. Okay, so that's just a very quick glance at what real-time physics looks like, just one example. I want to move on to looking at how can technology be used to, the same technology, be used to improve learning in lecture. And in lecture, we use something called interactive lecture demonstrations. Interactive lecture demonstrations are a strategy that can be used in a small class or a class as large as this, because they rely on having one set of equipment and using a strategy that engages the entire class. And I'll show you what that is. Excuse me. Okay. So to start out with, to show you what I mean by interactive lecture demonstrations, I'm going to show you an example of ILDs in mechanics. So here's how this will work. I will show you a demonstration and ask you to make predictions. I really will. So please, could you get out a piece of paper and a pen? Now, while I'm talking. Everybody. Piece of paper and a pencil or a pen. Okay? Don't worry. I won't collect these. I won't look at them. But it will help if you do this. Normally there would be a prediction sheet, but rather than print 1,000 copies of a prediction sheet, you can use your own paper. Sheet looks like in 1 second. One important point. When we ask students to make predictions, we never grade their predictions. We never give them a mark of right or wrong, because a prediction is what a student believes at the moment they make the prediction based on all the physics that they've learned up until that moment. A prediction cannot be right or wrong. It's based on what you know. So, and if you tell students that you will give them marks based on whether their prediction is right or wrong, they will not predict what they think. They will predict what they think you want them to say. That won't work. After you make your predictions, I will ask you to discuss your prediction with your neighbors and see if you can agree with each other. And then finally, I will do the demonstration and display the results, and I'll ask you to discuss it with the whole group. Now, normally, again, the demonstrations would be real experiments with real equipment, but I'm just going to show you pictures and the results so that I didn't have to bring equipment with me. All right. This is what a prediction sheet looks like. And don't worry about the writing on it, it's not important. You notice that at the top, it asks for the student's name, because often we take attendance to see whether students are there when we do these demonstrations. But they're not graded, when they know they're not graded. And there are places to put their predictions. Okay, don't worry about this one. This is the one that you're going to do. So here's the demonstration. So you have a piece of paper. Imagine, actually, let me show you the picture. So here we have the demonstration. There's a motion detector on the floor. I have a soccer ball. You all know what a soccer ball is? I have a soccer ball, and I'm going to toss the soccer ball up in the air and then let it come back down. Okay? That's the experiment. What I want you to do on your piece of paper is sketch a graph of the velocity versus time and the acceleration versus time for the soccer ball. You can forget about, don't worry about the throw, and don't worry about it hitting the floor. Just after it leaves my hand and before it hits the floor. So go ahead and please do that. I'll give you maybe a minute or two. Okay, I'm not going to give you a lot of time. What I'd like you to do now is turn to your neighbor, or 3 people together is okay, and compare your predictions. If you don't agree, then see if you can reach a consensus. So I'll give you about one or 2 minutes. Just with your hand, maybe like.
A velocidade começa num valor positivo. A partir do momento que larga a mão dele, se eu assumir um eixo positivo para cima. Por favor. Obrigado. É o segurador oficial. A partir do momento que larga a mão dele e assumir um sistema positivo para cima, então a velocidade é positiva para cima. Então ela sobe até então o valor é máximo na mão dele. E a partir do momento que larga a mão dele, a velocidade começa a diminuir. Então ela diminui numa taxa constante, que é a aceleração, sempre a mesma. O tempo todo uma aceleração negativa para baixo. Quando chega no ponto máximo, a velocidade chega a 0, e inverte o sentido, continua diminuindo, e chega a um valor igual ao que tinha na mão dele. Quando saiu, né? Só que invertido agora. Então é uma reta descendente, e a velocidade, e a aceleração é constante da gravidade.
Thank you so much. Okay. Another prediction. So,
eu acredito que os alunos não pensariam dessa forma. Eles colocariam talvez a velocidade sendo 0 na altura máxima, mas lá na altura máxima eles colocariam também a aceleração igual a 0.
Okay, thank you. Anything different? All right. Though I'll just tell you from my experience that one thing that students will surely try to do is make sure that the acceleration is 0 at the highest point. So they might draw an acceleration graph that looks like this: negative, 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 or other way, sorry. Positive, 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 0, negative, 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 negative. Or they might even draw negative, 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 0, negative, negative, negative. Because they are sure that the acceleration is 0 at the turning point. Okay, thank you very much. Let me turn this off because now I'm hearing Portuguese and I don't understand what she's saying at all. Okay, that worked okay. All right, here's what the graph looks like. next step, but I think I won't do that now because I don't want to take too much time on this. So let me, but the thing you can see, of course, what would you say, actually maybe we just, what would you say if I asked you to compare these graphs to the ones for the cart that went out and came back? What would you say? How do they compare? Similar? Same shape, yes? Why? What's common about these two motions? Okay, it's hard to do it by translating. Constant acceleration, yes? Both, okay. Let me go on. So, the procedure for interactive lecture demonstrations has 8 steps. Step number 1, describe the demonstration and do it for the class without showing the results. So in this case, I would have tossed the ball in the air and let it go to the ground. That's step number 1. Step number 2, ask the students to record their individual predictions. By the way, it's very important that the predictions are their own prediction. So when they're sitting there making a prediction, they should not be going like this. They should be doing their own prediction, because it's important that they say what they believe. Have the class engage in small group discussions. Ask for predictions from the class, from volunteers. Then the students can change their prediction if they like, record it on the prediction sheet. The prediction sheet will be collected. Carry out the demonstration and display the results. Ask for volunteers to explain the results. This is very important because if at this point I start lecturing to you, then students won't learn. The students must see that the results are in the graphs and that their fellow students can explain what happened. Not that I'm the only one who can explain it. So the results come from the students. And then there's a results sheet, which is a separate sheet. It looks exactly the same, and it's just a record for them to take home with them. And then finally, if it's appropriate, speak about analogous situations or applications. So in this case, the ball toss, I might have asked with the cart going back and forth, I would have asked, can you think of another motion that's like this? And students might say, tossing a ball in the air or tossing a penny in the air. This procedure is followed for each of the demonstrations that are on the prediction sheet. So maybe 6 demonstrations in one class. Now, for those of you I will tell you how to get this book. I'd be happy to tell anybody how to get it, but tomorrow in the short course I'll tell you. You can download the book for free. Unfortunately, it's in English. So if you want to use it, you have to translate. Okay, why do we use technology? What does it add to real-time physics and interactive lecture demonstrations? It allows for very clearly displayed observations of the physical world. And often these are made in real time. So something is happening, and at the same time as it's happening, the students see the graph. This seems to be very important. In fact, there was some research done that showed that was essential if they're going to learn. Many of these observations could not be done without the aid of computers. I remember the first time I saw the graph of a cart going up and down an inclined ramp. I looked at those graphs, same ones, right? Up and down an inclined ramp, same ones as we saw. I looked at them, and I had never seen those graphs before. Because we never talk about that. We do now. When I was an undergraduate, it was many years ago. Now even textbooks show some of these graphs. So some of these things we can't do very well without technology. But the important point is that the tools allow us to implement this active learning pedagogy. It's the pedagogy that helps the students to learn. The tools help the pedagogy, but without the pedagogy, there would be no difference. Because you can do the same experiment you've done for 20 years and use a computer-based tool and then tell the students about the result, they won't learn anything. It will be exactly the same as traditional instruction. Well, you should ask the question because do students learn from this? Is the learning improved? Because if the learning is not improved, then why waste our time and money? And for many, in the past, many innovations in education did not pass this test. Nobody ever tested. We physicists, when we find something exciting and different to do, or all scientists, not just physicists, something new and exciting that excites us, we think that will automatically excite the students and they will learn better. But you need to show that they learn better, otherwise why change the way you teach? So let me just give you an example of how we determine this. We do action research, which means research in our classrooms of student understanding of mechanics concepts. There's a test called the Force and Motion Conceptual Evaluation. It uses multiple choice questions that have been based on more open-ended research with interviews and open-ended questions. The questions are asked in a number of different contexts and forms. It makes possible to track what students understand about mechanics, mostly kinematics and Newton's laws, at various points in a course. And if you're interested in this, I'll talk more about it in the short course tomorrow, and there are a couple of research articles that I will give out that talk more about this test. But if you're not going to come to the course, just corral me and I'll give you more information. I just want to show you some results. So these are results actually from my university before we started doing active learning. The first two bars on this graph. So on this test, pre-instruction, the average score on the test was on the order of 15% correct. 15%. Okay, well, students just came into the course. If they knew everything, then why would we have a course? So we used to teach them in a very traditional way at my university. So after traditional instruction, this is the result, typical result. The learning gain is 8%. On the test at the end of the course, the students are only getting an average score of 20%. These are very, very basic questions in mechanics. And this is not just at my university. There are thousands and thousands of results that are published that are similar to this. After doing 2 sets of ILDs, that means 2 lectures, one on kinematics, one on Newton's laws, the learning gain is 74%. After doing real-time physics, which is a comprehensive curriculum on mechanics, the learning gain is 88%. So there's quite dramatic data that shows that students learn from doing these things. Why are these curricula effective? Well, if you ask students to make predictions, they have to consider what they believe at that moment before they make observations of the physical world. So number one, we're building upon what they know. We're not ignoring, we're not assuming they know nothing, because students who come into a high school physics class know a lot. They've done a lot of experiments in physics. They ride bicycles, they run, they walk, they climb stairs. Those are physics experiments, and they've reached conclusions from those. So they have ideas in their heads. So it's important that they first say what their ideas are. When they're asked to make predictions, defend their predictions in a small group, and write down their predictions on a sheet of paper that will be collected, they take it seriously, and they want to know the result of the experiment. They are engaged in the learning process. In many, many cases, students who make incorrect predictions or predictions that don't describe the result are certain that their predictions are correct. So when they see the result, there's what psychologists call a disequilibrium. They are very surprised. How come my prediction is not correct? And this is the opportunity to learn. And if the information is presented in an understandable way, then this is the opportunity for students to learn from the physical world, and it's also building their confidence as scientists, because that's what scientists do. They learn from the physical world. Okay, so much for computer data acquisition tools. I want to move on to the next topic. Clickers. You know what clickers are. Students have a little device. You ask them a question, they can pick one of the choices, right? And you can display a histogram to see what the students know. And many people use these. They come into class, they ask the students a question, they do the clickers show that the students don't understand it, and then they say, look, you don't understand, now I'm going to lecture to you about this. But the way that we use clickers is we use them with interactive lecture demonstrations. Instead of writing a prediction on a sheet of paper, why not make the prediction with a clicker? It's more anonymous. You can't go like that. It gives a collection of results automatically, so it's a very nice use. So let me show you how we do this. Okay, I already said that. It's very popular in the US. So what are effective ways to use clickers? That's the question. So I'm going to show you another example of interactive lecture demonstrations. I'm probably not going to ask you to make predictions, so you can relax. This one has to do with optics, image formation. And in fact, it's very low tech. It doesn't use computers for the demonstration. It does use the computer for the clickers, but okay. So let me tell you what these are about. Physics education research shows that the majority of students in an introductory physics course taught in a traditional way, before and after instruction, do not understand the function of a lens. They do not understand that every point on the object emits or reflects an infinite number of rays in every direction, and that of those infinite number of rays, the ones that hit a perfect lens should be focused, coming from one point on the object, are focused to a corresponding point on the image. That's what a lens does. So what we do for the demonstrations is to use miniature light bulbs, they're actually flashlight bulbs, and a cylindrical lens so that you can see in 2 dimensions what's going on. So let me show you that. Okay, so first of all, this is what the clicker question looks like. Again, I'm sorry you can't read it, but this question asks, you have an object. It's outside the focal point. You have a lens. It's a converging lens. Which one of these is the correct ray diagram? Okay? And there are 5 choices. All right. Here's what the apparatus looks like. There's an arrow. On the top of the arrow, there's a light bulb. On the bottom of the arrow, there's a light bulb. And there's the lens. It's just an acrylic cylindrical lens. If I turn on both light bulbs, this is what I see. And we can block one of them or put a color filter in and determine that the light from the top bulb is going to the bottom and the light from the bottom bulb is going to the top. So there is the image. That's where the image is located. You can see the light has been focused to those points. Okay? 2 point sources end up light focused to 2 points. Okay. Now, let me tell you before I show you the next prediction, how do we modify the ILD procedure? You remember it had 8 steps. Well, we modify it slightly because, so we describe the demonstration, so we show them the apparatus, but we don't turn on the bulbs yet because we want them to make their first prediction, the one about the ray diagram. Then, after they've done that, we'll go on to the next prediction, which I'll show you in 1 second. We ask the students to make their predictions with the clickers, but we don't show them the histogram of the results because we want them to have a small group discussion. And if you show them the results of the whole class, then that will influence their discussion. So we let them have their discussions, and then we come back and we have them record their individual predictions again, a second time. And this time we show them the histogram so they can see what the whole class did. Then we do the demonstration. We ask for volunteers to describe the results. They can record the results on a piece of paper. They don't get a result sheet. And then again, if there are analogous situations, we bring those in. So the last 3 steps are the same as before. Okay, this is demonstration number 2. What happens if I block the top half of the lens with a card? I block the top half of the lens with a card. Okay. Now I'll just tell you, you probably are aware of this, that the majority of students, when asked to make a prediction like this, will say either that half the image disappears or the entire image disappears. Those are the most common predictions. I'll explain why in a second. Well, here's what happens. So they make predictions, they go through the whole process. Now we're showing the result. I'm blocking the top half of the lens. And you can see the image is whole. The image is in the same location. The image is the same size, but it's dimmer. And they can see this. Again, I'm not going to lecture to them. They're going to tell me at this point what they see. And can you see why? Because the bottom half of the lens still gets light from both point sources. Okay? What about if I block, you might imagine that the next prediction would be, what happens if I block half the image? Well, if I block half the image, what happens if I block half the object? If I block half the object, then no light from the object reaches the lens. So then half the image goes away. Okay, by the way, I said I would explain to you, why do students think that you'll only see half the image when you block half the lens? we believe the reason is that students think in terms of ray diagrams. And you know, when you draw a ray diagram, you draw 2 rays, maybe 3 rays. But let's suppose they drew 2 rays. You know, the common rays parallel to the axis, through the center of the lens, through the focal point. Let's say they drew 2 of those. And then they block half the lens. One of those rays is blocked. Has to be. And then students find themselves, what happens now? There's only 1 ray. Does that mean we have half the image because instead of having 2 rays, we have 1 ray? Or does that mean we have no image because 2 rays don't intersect? So they are in a confused state because they don't really understand the idea of an infinite number of rays. Okay, this is what the computer display looks like in the software that we were using when we did this. You see it gives a histogram, it gives the percentage who answered each question, and you can see the correct answer, you won't remember, was D. So when the students made their prediction, only 30% gave a correct prediction. Then they had their small group discussion, and look what happens. You see the 30% there? After the small group discussion, it went to 40%. Okay, because when students discuss things, they often learn from each other. This is the basis of peer learning, that students can discuss things and have things make more sense just by discussing them. But with the interactive lecture demonstrations, I'll show you in a second, they do much, much better. Okay, do students learn from these demonstrations? Well, there's a test that we developed called the Light and Optics Conceptual Evaluation. It's the same type of test as the Force and Motion Conceptual Evaluation. There's one set of questions. It's about 40 questions, but there's one set of questions that we particularly look at. There's an object, there's a lens, there's a screen. You can see that the image on the screen is inverted. And then we ask, what happens? What happens if you move the lens further away? What happens if you take away the lens? What happens if you block half the lens? What happens if you block half the object? Those are the questions that are asked. And here are the results. So pre-test results, the students do significantly better on image formation questions on the pre-test than they do for mechanics questions. So about somewhere in the 40% range. After traditional instruction, the learning gain is only 20% on these questions. After the clicker ILDs, the learning gain is 59%, from the pretest. And we also have done this with paper and pencil ILDs, and the learning gain is still even better. It's upwards of 80%. So students do learn from these demonstrations. Although it appears that with clickers, the learning gain is not quite as big. There's another question on the test. This is a strange question. It's really a ray diagram, but it's a strange ray diagram. You see, the students are given 2 rays from the top of the arrow and 2 rays from the bottom of the arrow. And they're shown where the image is. And the question just says, continue these rays and show how the image is formed. If you understand what a lens does, then you know that any ray from the top of the arrow has to go to the image point of the top of the arrow. And any ray from the bottom of the arrow has to go to the image point on the foot of the arrow. These are not special rays. They don't go through the focal point. They're not parallel to the axis. But instantaneously, you should know where they have to go if you understand what a lens does. After traditional instruction, only 1/3 of the students can do this. After one lecture of clicker ILDs or regular ILDs, more than 3/4 of the students will get this question correct. Okay, let me move on and talk about 2 other technologies. Do I have maybe 10 more minutes, 15 more minutes? Okay, all right. Video analysis. Video analysis is very nice because you don't need any equipment. All you need is a computer. We don't think about computers as equipment anymore. Everybody has a computer. All you need is a computer and software. I'm going to show you an example from real-time physics, electricity and magnetism. And you may be surprised because if you've seen video analysis before, you've probably seen it used in mechanics because that's the most common use. If you have a video of any object moving, you can analyze frame by frame where the object is and analyze that motion. But in this case, the video is used to do an experiment on Coulomb's law. So let me show you this. We all know that doing experiments on electrostatics in the laboratory, in the introductory laboratory, is almost impossible to do. Now I know here it's not ever humid, so it's not a problem, right? No, I'm sure you can't do electrostatics here almost ever. So here's the lab. It's a lab called Electric Charges, Forces, and Fields. So first we have students do some simple observations with electrostatics, and we do observations that involve the biggest transfers of charge that we can get. So, you know, these experiments with Scotch tape, Scotch magic tape, they seem to transfer more charge than when you're using rods and little pith balls and things like that. So those work okay. Styrofoam cups and nitrile gloves, you can transfer a lot of charge. So you can make some observations. But then we quickly move on to an observation of Coulomb's law. And here's the what the apparatus looks like. There's a charged ball that's hanging. It has charge on it. And there is a prod with another charged ball on the end of it. And what we want to do is move the charged ball on the prod closer and closer, and of course you know what will happen. The other charged ball is repelled because they both have the same sign of charge, and it is pushed upward along an arc, okay? So that's the experiment. And the students can look at this and analyze it and come up with the mathematical relations that are needed to analyze the data. I won't go into that with you. Here's the video. So you see, okay, so we have about maybe 20 frames in this video. And what we can do with video analysis is mark where is the prod and where is the ball in each successive frame. And when we do that, we can calibrate this in terms of distances in units of meters, and we can collect the positions, and we end up with a table of data. So there's the table, all the data that was collected, there's the video, and there's a graph of, so what we've done mathematically is translate the data. The distance between the two balls is r, and we can calculate the force basically based on the angle. And so we're plotting force versus distance. And we can analyze this and see that it is some kind of inverse relationship, and the data are good enough to see that it's actually a 1 over r squared relationship. So this is very nice, and you can't do this any other way in an introductory lab. Okay, one last thing. One last use of technology, and this one is very new. There is a device called IO Lab. And what it is it is a relatively inexpensive $100. In the US, that's relatively inexpensive. Computer-based data acquisition system. It was designed by Matt Sellin, who's a physicist at the University of Illinois. Not developed by me. And there's a publishing company, Macmillan, which is responsible for producing these things. The idea is that if students can buy one of these in the bookstore and have it at home, they can do lab experiments or they can do pre-lecture activities. They can do little experiments and then come to lecture having done some experiments. Now, it's more expensive than a clicker. We routinely have students buy clickers. They cost maybe $25, $30. This is more expensive, but when you consider that a textbook in the US costs $250 or $300 now, this is relatively inexpensive. Okay, so that's the idea, that students can do experiments at home. The project that I'm working on with 2 other colleagues is to try to take real-time physics labs and turn them into labs that can be done with this device. Let me tell you a little bit more, because this is actually, in many ways, a fairly amazing device. It's a wireless unit. So it has a range of about 30 meters. There's a little dongle. Is there a word in Portuguese for dongle? I don't know. You plug into your computer, and the I/O lab transmits signals to the computer. It rolls on 3 wheels. There's an optical encoder inside the I/O lab that records position. Well, it actually records angular position and translates that into linear position. So we have real-time data collection, and there are some simple analysis tools in the software. It's a lot more than that. It has a force sensor. It has a light intensity sensor. It has an atmospheric pressure sensor. It has a microphone. It has a temperature sensor. It has a 3D accelerometer. It has a 3D magnetometer, and it has a 3D gyroscope, all built into this thing, and other things as well. Let me show you what an activity might look like. So this is actually an activity that was taken out of real-time physics. It's the first activity that students do when they start looking at Newton's laws. And the idea is, suppose that I pull and push on a cart, and I record the force and the motion at the same time. Can I see whether velocity is related to force or acceleration is related to force? So what's the difference? Well, acceleration related to force is Newton's second law. Velocity related to force would be an Aristotelian view of motion. So it's important initially to see which ones are related to each other. Okay, you'll notice, although I know you can't read this, the first thing it does is ask them, make a prediction. Which will be related to each other? And explain how you made your prediction. Okay, then they collect the data. And one nice thing, the software is set up so you can have like a notebook which has instructions, predictions, and everything on one side, and the observations on the same page. So here are real measurements by pulling, pushing, pulling, pushing. And if you look at those graphs, the top one is the force, the middle one is the velocity versus time, and the bottom one is the acceleration versus time. And I think you can see that the acceleration versus time has exactly the same shape as the force versus time. The velocity versus time has a different shape. That's not enough to teach students Newton's laws, but it's a start to see what things are related to each other. Okay, this project is continuing, and we're doing testing with students to see how these labs work. We've had some encouraging results so far, but there's still some things that are troubling, but they have more to do with the software and the hardware than they have to do with the basic premise of student learning. Okay. So the message I tried to bring you is that technology can help to put your students at the center of the active learning process, but only when it is combined with robust active learning curricula. So thank you for your attention, and I'd be happy to answer questions.
Perguntas? Tem alguém levantou o braço aí?
Eu queria saber se...
Just barely. Wait,
Alô?
Okay.
Eu queria saber, quando a gente não tem a resposta da turma como a gente gostaria, qual a tática que se usa?
For example, if I'm doing ILDs with a class and I pick a volunteer and they don't give the answer that I'm looking for, I will ask them more questions. It's just really the same thing we do in real-time physics, where we basically know what are the misunderstandings and we ask a lot of questions. So, for example, if they say that they still think the acceleration should be 0 when the thing turns around, what could I ask them? I could ask them, how do you calculate acceleration? And they'll say, hopefully, acceleration is the change in velocity over the change in time. And then I ask them, if you calculate a change in velocity, how many velocities do you need? And they say, well, of course I need 2. And then I say, well, suppose one of them is 0. Could there still be an acceleration? And they think about it and they look at the graph and they realize that the velocity before or the velocity after is not 0. So there is an acceleration. So that kind of thing, I would just ask more questions. And usually that works, okay?
Só minuto só, queria informar a todos que a gente vai fazer um atraso de 15 minutos para começar a próxima atividade, que são as mesas redondas, e a gente pode continuar, que essa a gente estava previsto para terminar 3h30, são 3h37 no meu relógio, então vai fazer um atraso de 15 minutos, e por favor podem continuar.
Thank you for your information. I believe that I've had the experience that everything in Brazil and all of Latin America starts late, and my talk started at 20 minutes after 2. So, but I'd be happy to be finished if you tell me to be finished. It's okay.
We still have more time.
Hello, can I ask in English?
You confused me.
Yeah, about ILD and the clickers. There's something going on in education right now that students work with their own devices connected with the internet. For example, cell phones or tablets or even computers. I'd like to ask you about the research itself. For example, the clickers. Can I For example, there are a lot of tools that collect data instantaneously from the class, and you can work with them and show the students about that. Is there something going on that you are studying about this, like replacing the clickers by students work with their own devices, connecting data through the internet?
It's harder to hear you because it'd be easier to do it in Portuguese.
For example, is there another
Well, they could hear it. No, go ahead. That's better.
about the clickers?
Yes.
For example, there are a lot of going on in education right now. The students work with their own devices, connect to the internet. For
Sure.
example, cell phones,
Cell
tablets.
phones, sure.
Yeah, and is there something going on in research about that? Because I have a fun research about that with tools through the internet to collect the data and show students what they're doing.
Yeah. Okay.
A pergunta
Ok,
então é sobre o uso os estudantes terem seus próprios equipamentos e usando a internet, fone celular, esse tipo de coisa.
So his suggestion was that there are tools available that use cell phones and use the internet to record the data, and this is true. And
I haven't used them, but the only thing I say to you is,
and I said this at the beginning, the things that we've designed and the things that we've used are very simple to use and are fairly foolproof, student-proof maybe. And it's very important that the student's time is spent making observations and not trying to figure out how the thing works. So if it works, if it's robust, it works well, fine. There are lots of other things out there. I'm not saying you have to use these. But it must work well. Otherwise, because if you get messed up with the details of the software and hardware, the students won't learn anything. Okay.
Aí, ok. Eu queria saber, quando o professor pediu para fazer as previsões, eu não entendi se era para nós fazermos como alunos ou o que os alunos pensariam. Por isso eu dei a resposta. E tem uma outra coisa, segunda.
Yeah. No. For a group like this, that's why I give your own prediction or give what you think students would predict. For a session like this, either is good. It was fine. Yeah.
E a segunda coisa.
Wait. Go ahead.
Segunda coisa. No ensino médio, também há pesquisas sobre essa aplicação desses mesmos métodos. Se existem pesquisas sobre essa aplicação no ensino médio nos Estados Unidos.
Yeah, these things have been used, both real-time physics and ILDs have been used in high schools. There are data that show that there are good learning gains. I don't know if they've been published or not. I didn't do the research. But we've had lots of high school teachers in many different projects using these same tools. They're really, in the US, most students who take physics take it in their last year in high school. And the difference between a student in the last year of high school and a student in the first year of college is not very much. So I know perhaps in Brazil it's different, because I was told that in Brazil, students take physics every year in high school, but only maybe 2 hours a week. So So I think maybe in the earlier years of high school, some of these would be difficult for students, but in the last year, they should work quite well.
More question?
Wait.
Okay. So,
eu tinha só um questionamento em relação à referência que o senhor utilizou do peer instruction em relação à única metodologia ativa que o senhor citou. Minha pergunta é mais direcionada se existem outras referências utilizadas, como o Linear-Based ou metodologias ativas de uma forma geral que seja usada na sua universidade ou de uma forma geral nos Estados Unidos.
So, yes, there are other methodologies. Well, I mentioned, for example, peer learning. Peer learning is an active learning strategy that was developed by Professor Mazur from Harvard, and it involves students having small discussions in a lecture class. So it's a very active use of an environment with a large number of students. In many ways, it's similar to interactive lecture demonstrations, except there's no demonstration. There are other strategies that would be characterized as active learning. Really, anything that there are tutorials from the University of Washington, for example. There are many other. The answer to your question is yes. There are others. I chose in my talk to present, number one, ones that use technology, and number two, they are ones mostly that my colleagues and I developed. But there are others that have the same basic ideas, namely having students make predictions, having students discuss things, peer interactions. Those are important for all active learning strategies. Okay?
Ok, vamos agradecer então novamente.
Alô? Só mais uma pergunta. Aqui no Brasil, eu acredito também lá nos Estados Unidos, a gente tem um ensino de física, a parte conceitual, que o que o senhor apresentou aí é muito bom para a parte conceitual, mas também aqui nós temos a parte analítica, né, a parte matemática, onde a gente precisa calcular as coisas, né? Então, talvez, assim, eu não vejo como utilizar esse tipo de tecnologia para ajudar na questão matemática, né, dessa habilidade em responder, por exemplo, calcule a força, calcule a aceleração, calcule, entende? Para a parte conceitual, ótimo, é muito bom mesmo. Mas e o outro lado, né, o lado mais analítico, como que fica?
Right. Okay. So, I said. Actually, let me quickly. Hello. I won't bother. On
Almost the very first slide, I said that these are methods to help conceptual learning, but they are complementary to the more quantitative parts of physics because we don't throw that away. So, these are not completely non-quantitative. Real-time physics labs are very quantitative.
There's a lot of things that students do that are similar to what they would do in any laboratory. But one important goal of those labs is to learn the concepts as well. In my physics course, I do interactive lecture demonstrations one time each week. The rest of the time, I am spending on more quantitative things. We have in my course a collaborative tutorial where students meet and work in groups on problem solving. This is how we help them develop problem solving skills. So we're not neglecting that at all. It's just the part of physics that has been neglected And the research that came out starting in the mid-'80s showed that students who could solve every problem in the textbook could not answer the simplest question about Newton's laws. So that's why we put more of an emphasis, but that's not to say that this emphasis replaces the problem solving. It's the problem solving, the mathematical is of course very important, depending on what is the level of the course. But the general physics course, yes, of course you have to do that. So, yeah.
Ok, vamos agradecer novamente. Só espero vocês um minuto para fazer alguns avisos. Vamos agradecer então, professor Sokoloff.